how many different 4-letter words can be formed using only the first 10 letters of the alphabet? Okay, so that's one type of question we have usually in counting principle, using counting principles, making words, you know, it's 4-letter here, maybe it can be different number of letters. In each counting principle, there are two things we need to be careful about. The first thing is, do we have an order in this problem? And the second one is, do we have repetition? So that means, can we use an object multiple times, and is there any order in this problem? So when we face this kind of word making problems, so the order is obviously true, so we have an order. We have the first letter, second, third, and the fourth letter. Okay, there is an order. It's not actually, you know, there's, if you have two words like AB and BA, these are different words. Okay, we cannot say AB and BA, they are the same words. So that means it's important which letter is at first, which letter is the second letter. Okay, so that's the definition of order. So in word making problems, we have an order. But what about repetition? Can we repeat a letter multiple times? So that depends on the question we have. For example, here, part A of this question says, we're going to count the number of different words if there is no restriction on the letters used. So what does it mean when it says there's no restriction? That means we can use a letter multiple times. Okay, so if the first letter is A, the second letter also can be A. So how can we do this? Part A. For part A, we can use 10 letters as the first letter. It can be any of those letters A to J. What about the second one? Again, 10 cases, 10 different letters. Okay, 10 here and 10 here. So that means for part A of this question, we have a situation which there is an order and we have repetition. That means the letters can be repeated each time. So in this case, it is, we using the multiplication principle. So it's just 10 times 10 times 10, and the answer is 10 to the power of 4. And this logic can work in any problem when we have order and we have repetition. So when you have a bunch of objects and you're going to choose like when you have n objects and you're going to choose k objects, and there is an order in this k object, and the objects can be repeated. So what is the answer? So for the first object it can be n, the second one n, the third one n, to the kth one it can be n, so it's just n to the power of k. So that's for generally solving a counting problem when there is order and there is a repetition. So let's talk about the part B. So part B, it says if the used letters are all different. Okay, so now there is a restriction on the problem. Okay, so it says if you use a letter for the first letter, okay, so it can't be using another letter. Okay, so each letter can be used only once in the word we have. Okay, in the word all the letters are different. So how can we do this one? For part B, still we have the order, but what about repetition? We don't have it anymore. Okay, so that's going to be again 4 places. The first one, we have 10 choices. Any of those 10 letters can be here. Since we already selected one letter for the first letter and the letters must be different, we have only 9 choices for the second letter. What about the third? We already used 2 for A for the first letter and the second letter. So we have 8 choices here and 7 for the fourth one. So again, we use multiplication principle, and that's the solution. Okay, so it's just 8 times 10 times 9 times 8 times 7, and generally we can use this problem. Okay, so it is 10 factorial divided by 10 minus 4 factorial. Okay, so which is actually 10 factorial by 6 factorial. Okay, so it is the general formula. So what is it, part B? Part B is when we have an order but we do not have the repetition. Okay, the objects cannot be repeated. You can use an object only once. The objects in each place must be different. So now we can use this formula, which says n factorial n minus k factorial. This formula works for when we have n objects. We want to choose k objects in an order and we do not have repetition. So we use this formula for this one. Part C. How many different words can be formed starting with a vowel? Okay, so here is, we're gonna find different words, but here they didn't say anything about repetition. That means we have repetition. Okay, a letter can be used more than once. Okay, so but the restriction on the problem is the starting letter. Okay, so it says, okay, it starting with a vowel. Okay, so now let's see how we can solve this one. For part C, still we have 4 places. We have the order for the first, as the first letter. Okay, how many choices do we have? Okay, it says the first letter must be a vowel. Okay, so how many? So if you just look at the letters we have, A is a vowel, E, and I. Okay, there are only 3 vowels here, and we can use any of these 3 letters as the first letter here. Okay, so we have 3 choices for the first one. What about the second letter? Okay, so here we have repetition. The letters can be repeated, so we can use any of those 10 letters as the second one. Third one can be 10 and then 10, and again we have multiplication in between, and therefore the answer is 3000. Okay, so there's no formula here when we have the this type of conditions. Okay, it doesn't say anything about the repetition. Okay, so it's kind of mixed problem, so we have to just count it directly. Like here there are 3 choices for the first letter, and you just talk about the letters one by one, what happens, and then count the numbers, which is here 3000. Okay, what is the first one? So if the part D of this counting problem, okay, it says how many different words can be formed if the first letter is followed by 2 consonants, then a vowel. Okay, so it doesn't say anything about the first letter. It doesn't say anything about the first letter, but if the first letter is followed by 2 consonants, then a vowel. Okay, so here there is an order here. So that means the first letter, it can be any of these 10 letters. Okay, but the second one, the second letter must be any of these 3 vowels. and then the third and the fourth letters must be consonants. Okay, any of these 7 letters. Okay, so we can just count it like what we did at part C. So for part D, again, we have orders. The first letter is, we have 10 choices, any of these 10 letters. For the second letter, it can be a vowel, so it's just 3. And then for the other 2 places, this one and this one, they must be consonants. Okay, so it's just 7 and then 7 here, and then we multiply, and that's going to be the solution. So how many it is, just I use the calculator. 49 times 3 and times 10 is 1470 different words we have. Okay, so it was part D. Okay, the part D of the question says we're going to count the number of letters, the number of 4-letter words. The first letter, there's no restriction, so we have 10 choices. For the second one, it should be a vowel, so 3 choices. And for the third and the fourth one, we have 7 and 7. Okay, they must be consonants. The place of vowel and consonants in these words has been mentioned. Okay, we know the second letter is vowel, the third and the fourth are consonants. But let's say, what if we can just make a new question here? What if we don't have any we don't have any constraint on the first one, but in the next 3 letters we know one of the 3 letters here, one of them is vowel and the other 2 are consonant. We don't know which one exactly is the vowel, okay, and which ones are consonants, but we know one of these 3 would be vowel and the other 2 will be consonant. Okay, so how can we do this question? To solve this one, we can say, okay, it's a little bit different. Here we can talk about the difference between multiplication principle and addition principle. So in part D of the question, we put some multiplication here. We said it's a multiplication principle. What is the reason? Because the reason is we have actually 4 actions here. The first one is selection of the first letter. The second one is selection of the second. Selection of the third letter is the third job. And selection of the fourth letter is the fourth action must be done. But the question is, what the whole situation is, when we're going to make a 4-letter word, we have to do all these 4 actions at the same time. Okay, if we're going to have a 4-letter word, we need to select the first letter, second, third, and the fourth one. So because all these 4 jobs must be done at the same time, we do the multiplication. So why I'm still talking about this, the reason is for the new situation, when we say we don't know which one of these 3 is a vowel, which one of the other, which one is a consonant, here is the difference between multiplication and addition principle. Okay, again, we have the order. The first letter, it can be any of these 10 letters. But what about the vowel? Okay, we have these situations. It can be, vowel can be here, and consonants, these 2. We can have consonant here, vowel, and then consonant, and we can have consonant, and the vowel at the last letter, for the last letter. Okay, so we have 3 situations here. Okay, but here, any of these 3 situations, the first one, the second one, and the third one, these 3, they cannot happen the same time. Okay, so if you have a word, a 4-letter word, it cannot be the first one and the second one at the same time. Okay, you have a word, okay, it can be, the vowel can be at the second letter, as a second letter, or the third, or the fourth one. We cannot have a 4-letter words when we have only one vowel, and it can be at the same time for the second and the third one. Okay, so these are these three situations, 1, 2, and 3. Okay, they are the situation, they cannot happen at the same time. So that's why we're using addition principle here. We say, okay, we count all the words for the first one, second one, how many words we have with the second one in the second one situation, and how many words in the third situation, and then we add them up. But in each situation, this one, we multiply 10 by 3, then 7, and then 7 here. For making this type of, for first situation, we use the multiplication principle. So it's going to be, for the first one, we can say, okay, just we have vowel, so 3, then 7, then 7 here. For the second one, which we have consonant, vowel, and consonant, again we have 10 for the first one, we have 10 for the first letter, 7 for the second letter because it can be consonant, and then 3 for the third, and 7 again consonant for the third one. What about the third situation, which is consonant, consonant, vowel? So again, first letter is 10, 7 here, 7 here, and the last one, it can be the vowels, which we have 3 situations, 3 letters, so it can be 3. So how many ways we can do this one? So it is 1470 for the first one, plus 1470 second one, plus 1470 for the third one, which is 3 times 1470, which is 4410. Okay. Now, how can I formalize this one? Okay, for this situation, we can count it by this visually. Okay, that's what happens here is 10, 7, 7. Okay, but how can I do this question a little bit more mathematically? To solve this one more mathematically, okay, so we can say we have 10 choices for the first letter. Okay, so we can say 10 here, but for the other 3 letters, okay, first thing first, we need to choose which letter must be vowel. Okay, it's one of the 3 letters, the remaining letters. Okay, so we say, okay, it's one of the 3 remaining letters is a vowel, and the other 2, which is choosing 2 of 2, combination 2 of 2, and then it's just for any of this. Okay, when we say 1 out of 3, it says, okay, which one of these 3 places is a vowel. Okay, when we choose the other one, the other 2 will be a consonant, so that's why it's 2 out of 2, combination of 2 out of 2, so that means it's just 1. Okay, so if you just choose the vowel, so the place of the other 2 consonants will be already none. So here and for each of these situations, okay, when you say one type combination of 1 of 3, so that means it's just 3, and then 3 times 3 for the vowel, times 7 for the first consonant, 7 for the second consonant. So here we can do this question generally like 10 times 1, combination of 1 of 3, combination of 2 of 2, and then times 3 times 7 and times 7. So the answer will be the same as before, 4,410. Two dice are tossed and the magnitude of the difference in the number of dots facing up in the two dice is noted. Okay, so in this experiment there are two dice, okay, and what's important is the difference in the numbers observed. So here now what we want is just part A. It says what is the sample space. Okay, so we are tossing two dice, so how many results can we see? 6 times 6 is 36, and what are they? That's very easy. The sample space S is going to be, okay, so we just have to write which numbers we will have for the first die, which numbers for the second. Okay, six numbers for the first, 6 numbers for the second, so it's going to be 36 in total. So like we're gonna have 1 1, so here the first number is just for the first die, the second is the result for the second die. Okay, so now 1 1 1 2 2 1 6, and it can be 2 1 2 2 2 6. These are the result when the number for the first die is 2, and for the second die it can be 2 1 2 and 6. My bad. So here is 2 2 6, and the last row is just 6 1 6 2, and it goes to 6 6. These are all the possible results when we toss two die. It is as the sample space for this experiment. Now for part B of the question, it says find the set A corresponding to the event. What is the event? The magnitude of difference is 3. It's exactly equal to 3. So now if you're going to find this, it was A. For B, the event A is all the possible values, which when we find the difference of the observed number and the magnitude, that means the absolute value. If it is positive, that's it. If it is negative, just multiply it by a -1. So like for example 1 4, so that means the first die has 1, the second die is 4, so the difference is 1 minus 4. Okay, so 1 minus 4 is -3, but the magnitude means absolute value, which is 3. So that's it. So here 1 and 4 is one of the answers, so 1 4, and also 4 1. The other one is just 1 2 5 5 2 and 6 3 3 6, and I don't think there's any other result which it can be 3, okay, as the magnitude of difference. So that's the event A. So what about part C? Part C of the question, it asks for an event B, which corresponds to the event magnitude of the difference is larger than 3. Okay, not even equal. Okay, larger than 3. So it can be when we have 1 for the first die, it can be not 4, but it can be 5, and also 5-1. One five five one. It can be 1 6. Six one. It can be 2, not 2 5, but it can be 2 6 and 6 2, and that's it. Okay, what is the other part? It says part D of the question. It says find the set C corresponding to the event magnitude of the difference is larger than equal. Okay, if you just look, part A was the set A was magnitude is equal to 3, B is magnitude is larger, and for C is larger or equal. So that means the event C is the union of A and B. So part D, we have an event C, which is A union B. So now we can just put all the elements in A and B in just one set, and it's going to be C. So it's just 1 4 4 1. Okay, and it is C. In the last term, the 150 students enrolled in a program took at least one of the courses, programming, a calculus, or a course in linear algebra. In addition, 60 of these students took a course in programming, 60 students took a course in calculus, and 105 students in linear algebra. Finally, 15 students took a course in programming and calculus, 30 a course in programming and linear algebra, and 40 in calculus and linear algebra. Determine the number of students who have taken the 3 courses. So for this question, we are going to use a formula, which is the relation between probability of union of some sets and intersection of sets. How can we solve this one? So let's read the question again, highlight the numbers and the main part of the question. So here it says 150 students enrolled in a program, okay, and they must take at least one of these courses. So it means 150 students is the total number of students. They take at least one course, okay, so that means there's no students with any no course taken, okay, so all the 150 students, they have taken at least one course. One of these 3 courses. The first course is programming. We use P for programming, the students who take programming. C for calculus, and H for linear algebra. So now here are the information, okay. First part is there are 60 students, they take course in programming, so we can just say N of P, number of students take programming, so it's just 60. What about the next one? The next part is 60 students took a course in calculus. 60 students in calculus, so N of C, and the number of students in calculus is 60. The next part, 105 students, they enrolled in linear algebra. So n of h is 105. Okay. Now we have the intersection of each two of them. So the next part, it says finally 15 students took a course in programming and calculus. Okay, so that means 15 students, they've taken both. So here it means both courses, programming and calculus. So that means n programming and calculus. So we use intersection. It means students in programming and calculus. Okay, all the students which they enrolled in both calculus and programming. So what is the number? It is 15. The next part is 30 students, linear algebra and programming. So it is n of p, intersection h is 30, and the last one, n of c and h, that means calculus and linear algebra. So it is 40 calculus and linear algebra. So the number is 40. And 40 students. And what about 150? 150 is the total number of students. So it means n of n of p union c union h. So that means the total number of students. So that means total number of students, they enrolled in at least one of these courses, so it's just p union c union h, which is the total number of students, is 150. And what we're looking for is we are going to find the number of students who have taken the 3 courses. Okay, the students, they enrolled in all the 3 courses, so which means we are going to find number of students in programming and calculus and linear algebra. Okay, so now we can use the formula. Number of students in at least one of the courses, P union C union H, is equal n of p plus n c plus n of h. Okay, now minus n of p intersection c minus n of p intersection h and then plus again n of p intersection c intersection h. So that's the formula. So here this is the part we're going to find. So we just plug in all the other values here. So we're gonna have 150 is equal to 60 plus 60 plus 105 minus 15 minus 30 minus 40, and then plus n of p intersection c intersection h, which is the value we're looking for. So now it's going to be n of p, c, and h is 150 . Okay, so now if we use calculator, the value will be, so 150 minus 60 minus 60 minus 105 plus 15 plus 30 and plus 40. So the answer is 10. So 10 students, they enrolled in all the 3 courses. In this counting principle question, okay, it is about arranging some books in a bookshelf. So this question says you have textbooks. Here is important, okay, all books are different. Okay, let me highlight this part. All different, including we have 3 linear algebra books, 5 psychology, 4 sociology, and 2 economics. Okay, so it means, yes, we have 3 linear algebra books, but these 3 linear algebra books are different books. Okay, they're not exactly the same books. We have different books. So now the question is, how many different ways can you place these manuals on a shelf of your library? So now the question can be solved with different restriction. Okay, the part A of this question says, okay, just find different arrangement when there's no restriction on the question. Okay, so here what's important is, for this question there's no restriction, means actually, you know, all the books are different. So we can say we have 3 plus 5, 8, 8 plus 4, 12, 12 plus 2, 14. We have 14 different objects. It's a shelf of library, so that means there is an order. So it is just like 1, 2, 3, 4, 5 to 14. Okay, we have 14 places with order, the first book, second book, third book to the last book. So there is an order, and here it says there is no restriction on the question. But here what's important is, when you put a book in the library, you cannot put it for the second one. Okay, it's not like a word making question. You can use a letter multiple times. For this question, okay, once you use a book, so it's already in the library and you cannot use it another time. Okay, so that's a difference between word making questions and arranging books in the library. So that means we don't have repetition. The words can be, the books can be used only once. Okay, once you use a book, it's already gone. Okay, so you cannot use it for another place in the library. So we don't have repetition. We have order, but we want to solve it for different situation. Okay, situational problems. The first part, part A, it says there is no restriction for this. There's no restriction on the arrangement. That means they can be placed anywhere in this library. Okay, so for this one, and all the 14 books want to be in the shelf. Okay, so that means it's not we're gonna choose 10 out of these 14 books for the library. We're gonna put all the 14 books in the library. So how many ways we can do part A? Part A, we have 14 objects. We're gonna put them in the shelf. There is an order, there's no repetition, so that means it is 14 choices for the first place, 13 for the second, and 2 times 1. And you can see the answer is 14 factorial. So for a question, when there is an order for the arrangement, there is an order, there isn't any repetition, we cannot use an object more than once. So here we use factorial for solving the question, okay? It's just factorial. Okay, so what is part B? Part B of the question says, if the textbooks on the same subject are grouped together, okay? So that means we are going to have linear algebra books together next to each other, psychology books together, and economy books together, and sociology books together, okay? So how can we do this part B? To solve this one, so that means we need to choose 4 places, okay? We have 4, 1, 2, 3, 4, because we have 4 subjects. And first thing first, we need to choose which one of these 4 places is for which object, okay? For example, where is linear algebra books, okay? Linear algebra books can be here or here or here or here, okay? First, we're not talking about which book is, because we're going to talk about where exactly, all the linear algebra books are. So first we choose which one of these 4 places is for linear algebra, which one is for psychology, sociology, which one of these places is for economy. So first we choose place of group of books. How many ways? There are 4 subjects, and there is an order, okay? 4 places, there is an order, there is no repetition. That means we can choose which subject must be where by 4 factorial. That means by 4 factorial, in 4 factorial ways, we can choose which subject is. Okay, for each of these 4 factorial situations, okay, so let's say, for example, we have linear algebra here, we have psychology here, we have sociology here, or we have economy here, okay? That's one of these 4 factorial situations that can happen for this question, okay? Now let's say for one of them here, for these linear algebra books, okay, for this one, we know here are placed the linear algebra books, but there are 3 different linear algebra books. There are 3 different linear algebra books, okay? The books are different, so that means we have times 3 factorial for how we can place these 3 books here, the 3 linear algebra books here. What about psychology? For psychology, we have 5. So 5 times 5 factorial and for sociology it is 4, so times 4, and times 2 factorial. That's how we can just arrange these economic books. Okay, so it is the answer, okay? 4 factorial, that's where we can put each group of books. Here is linear algebra, psychology, sociology, economy. Then maybe it can be another way, okay? Maybe we have psychology here, then linear algebra here, sociology, economy, okay? So in how many ways these groups can be arranged? So it's 4 factorial. Then we can just arrange each book in each group. Okay, here we have 3 books, so 3 factorial. Here we have 4 books by 4 factorial. They can be ranged. Okay, here is 4 books, 4, and here is 2 books, so 2 factorial. So this is the final answer for part B. Okay, so what about part C of the question? It says if the textbook and the economy subjects are grouped together. Okay, so for this one, if you just compare part B and part C, so part B, it says the books in the same subject are grouped together, so that means linear algebra, psychology is together, sociology together, economy together. But part C, it just said only the economy books are together, okay, grouped together. So that means only these 2 books are next to each other, and for the other books in other subjects, so they can be next to each other or not. Okay, we don't have any restriction on the other books. How can we do this one for part okay. How can we solve part C? So here, in total, we have 14 books in 4 subjects. We're gonna have the economic books next to each other, grouped together, grouped together, okay? So that means if you just say, okay, for the other 12 books, there's no restriction, and we choose the 2 economy books as just one object, okay? Then we just say, okay, just let's say these 2 books, these 2 economic books, let's say they are just one object, and there are 12 other objects, okay, which are the other 12 books, okay? First book, and here is 11th book, 12th book, and here are economic books. Okay, so that means we have 13 objects. Okay, yeah, for economic there are 2 books, but first we choose where is the location of economic books, then we say, okay, in how many ways these economic books can be permuted. Okay, so we have 13 objects, 12 different books of the other objects, and the 13th one is just the economic books. For part C, it's 13 factorial, where these 12 books and the 2 economic books can be placed. So like, for example, we can have book number 1, then the 2 economic books, then 2, 3, 4 to the book 12 here. Okay, but what can happen for these 2 economic books? There are 2 factorial permutation for here. Okay, the book number 1, economic number 1 can be here, economic number 2 can be here, or it can be economic number 2 at first, then economic number 1. So there are 2 factorial arrangements for these two economic books. So the answer is 13 factorial times 2 factorial. Okay, here it says, okay, so how we can just arrange these books. Here we can just talk about, a little bit more general case, like what if we are going to have economic books grouped together and also linear algebra book grouped together. Okay, so that means linear algebra books be grouped together and economic books get grouped together, but for the other 2 subjects they can be anywhere in this shelf. So for this one, we need to choose one place for the linear algebra and another place for the 2 economic books. So it is 5 out of 14, so there are 9 remaining books. Okay, book number 1, 2 to 9. Okay, for the other 2 subjects. So now first we choose which one of these 9 books with along with these two other subjects. So that means it's 9, 10, 9 books here, 10 and 11. Okay, so we can say for each one we have 11 factorial. So we know now in 11 factorial cases forms, we can form these 9 books with these 2 subjects of linear algebra and economic books. So then we have to multiply it by 3 factorial to say where each linear algebra book is, then multiply by 2 factorial to choose where economic books are. So it is how we can solve if just one of these subjects are grouped together. Okay. So what about part D? For part D, it has if you place a psychology textbook at each end, okay, so we have 5 psychology books. We have 5 psychology books, and in each end, you know, here we have 14 places, place 1 to 14. Okay, so we're gonna have a psychology book here and another psychology book here, and there's no restriction on the other 12 books in between. So in how many ways? For the first book we have 5 choices. Okay, any of those 5 psychology books. We choose another psychology book for the other end. Here is 4 because we already used one for the left end. We're going to use one of them at the right end. So now we have only 3 remaining psychology books with the other books in different subjects. So here what we have is just 5, and then they must be multiplied by what? Then what about the other ones? It's like we have linear algebra. There are 3 books, so it's multiply 3 factorial times 2 remaining psychology books times 4 sociology books, 4 factorial. So actually here, instead of multiplying by subject, so we can just say, okay, we already used 2 books for each end. We already used 2 books for each end, left and right. So we have only 12 books. Now we multiply it by 12 here. So what is the total numbers? So it's just 5 times 4. So here's 12 factorial times 12 factorial. So that's all the forms. We can just place these 14 books in the shelf, 2 psychology books at each end. A number R is selected at random from the unit interval. Okay, so here we have unit interval, a number R selected from this interval. Then now we have 2 events. Event A is when, you know, is all the numbers in this unit interval which their difference with 1/2 must be more than 1/4. And event B is the event that for all the numbers R, which 1 minus R is less than 1/2. Okay, so we have 2 events. Now we're gonna find A union B, A intersection B, and A complement intersection B. So before solving these 3 parts, what we need to find A and B. Okay, what is unit interval? Unit interval is the all the numbers between 0 and 1. Okay, so the number set, if here is 0, here is 1, unit interval will be from 0 to 1. All the numbers right here. So that's the S, the sample space, or the unit interval, which is the unit interval here. Now, what is A? A is from 0 to 1. Here is 1 over 2. Now we need all the numbers in unit interval, which their distance, their difference with 1 over 2 must be more than 1 over 4. So you can see if here is 1 over 2, 1 over 2 plus 1 over 4. We have this number 3 over 4, and here is 1 over 4. Okay, so the numbers in this set, which their difference with 1 over 2, the distance with 1 over 2 is more than 1 over 4, more than 1 over 4, not even equal, okay, more than. So that's going to be 3 over 4 is not included because its distance, its difference with 1 over 2 is going to be 1 over 4, but we need all the numbers which their difference is more than 1 over 4. So it's just 3/4 to 1. 1 is also included because it's in unit interval. And the same here, the number 1 over 4 is not to 1. So you can see any number we pick here, okay, in this part or this part, you will see their distance to 1 over 2 is less than 1 over 4, okay? So because here is 1 over 4, here is 1 over 4, and the distance we need is more than 1 over 4, so the number selected, the number R, cannot be from 1 over 4 to 3 over 4, okay? And so it should be between 0 to 1 over 4 and 3/4 to 1 over 4. And we can just say A is set A, event A is in interval notation, it is 0 to 1 over 4, 0 included, 1 over 4 not included, union 3 over 4 not included, to 1 included. So that's A. We have another event B. From 0 to 1. Now R is the number which 1 minus R is less than 1 over 2. That means the numbers less than 1, which their distance to 1 is less than 1 over 2. Okay, what are those numbers? So here is 1. So if we just choose, here is 1 over 2. So 1 itself is if R is 1, 1 minus 1 is 0, is less than 1 over 2 is included, and it should be less than 1 over 2. It cannot be 1 over 2, so 1 over 2 is not included, but any number here between 1 over 2 to 1. So any number we choose here, its distance to 1, 1 minus R is less than 1 over 2. And we cannot choose any number here, because any number here, if you choose, 1 minus R will be bigger than 1 over 2. For example, if we choose 1 over 4, okay, which is less than 1 over 2, then 1 minus 1 over 4 is 3 over 4, which is bigger than 1 over 2, and it's not, 1 over 4 is not an answer here, okay? So okay, so that's B. If I'm going to write B in interval form, B is from 1 over 2, 1 over 2 not included, to 1 included. Now we found A and B, both events A and B. Now we can talk about these three parts, okay? So the first one is, what is A union B? A union B, it means all the elements which belongs to at least one of these sets, okay, A or B. Okay, so that means we put all the elements in A and B in just one set, and it gives us A union B. Okay, so now you can see we have A, we have B. Their union will be 0, 1. Here is 1 over 2, 1 over 4, and 3 over 4. Here is 1 over 4. Okay. Now, that means whatever we have in A, whatever we have in B, we put them all in one set, and that's going to be A union B. So here I can say this one, these two will give me A, and this is B. Okay, now A is from 0 to 1 over 4, and 3 over 4 to 1. Now what about B? B is from 1 over 2 not included to 1. Okay, so now we can see what is A union B. A union B is 0 included to 1 over 4 not included, and so here is a union, 1 over 2 not included to 1 included. Okay, so that's A union B. The only part which is not included is just between 1 over 4 to 1 over 2, which is not included in both A and B. Okay, so you can see it's not in A and it's not in B. So this part, so that means it's not included in A union B. So if it's like, you know, we put this part on this set, you can see we're gonna have this part and this part, that's A union B. What about the intersection? Intersection for part B, there's 1. For intersection, you will see that means all the common parts in A and B. So B is between 1 over 2 to 1, and this part is between 1 over 2 to 1. For A, we just have this one, so that's the intersection of A and B. So now we can just say, if you just look, you will see I drew both in just one graph, okay, to show how it works. B is here, that's B. And what about A? A is from 0 to 1 over 2 and 3 over 4 to 1. So which part is in common? So you can see here, for here there's no B, so it's not in common. This part from 1 over 2 to 3 over 4, there's no A. A doesn't have common with B. This part is the only common part between A and B. So we can say, okay, so the common part is from here to here, which is exactly the right part of A. So A intersection of B is going to be 3 over 4 not included to 1 included. What about the last part? For the last part is we're gonna find A complement intersection B. So we need to find A complement first and then intersect that with B. Okay, so what is A complement? First, 0 to 1. Here is 1 over 2, 3 over 4, 1 over 4. So A complement means anything which does not belong, any part which does not belong to A. So if you look here, from 1 over 4 to 3 over 4 doesn't belong to A, so that's going to be A complement. Now it is 1 over 4 is not in A, so it should be in A complement. 3 over 4 does not belong to A, so it's in A complement, and any number between these two. So that's A complement. A complement. Now we're going to find an intersection with B, so here is A complement. Now what is B? B is from 1 over 2 not included to 1, which 1 is included here, so that's B, and the intersection you can see is this part between 1 over 2 and 3 over 4. So A complement intersection B is 1 over 2 not included, because 1 over 2 is not in B, so it can't be in the intersection. 2, 3 over 4. 3 over 4 is included because it's included in both A complement and B. So that gives us A complement intersection B. In a restaurant menu, there are 5 choices for the entree, 6 choices for the main course, and 3 choices for the dessert. Now the question is, in how many ways someone can order a meal in this restaurant, including an entree, a main course, and a dessert? Okay, for a meal, this question for a meal, it includes 3 parts: entree, main course, and dessert. And these 3 choices for the entree and main course and the dessert, they must happen at the same time for the total action selection of a meal. Okay, so that means for each entree we're gonna have several choices of main course, and for each main course we're gonna have several choices for dessert. These jobs will happen together at the same time. So that means here we're gonna use the multiplication principle. So choosing a meal, okay, selection of meal is, it has 3 parts. The first one is the entree, the second one is the main course, and the third one is the dessert. So for the entree there are 5 choices, for the main course there are 6, and for dessert there are 3 desserts. So what is the total number of options here? It's 5 times 6 times 3. And the answer is 90. So there are 90 options for a meal, okay, including entree, main course, and dessert. So here we have 3 events A, B, and C. Now we're gonna find the expression based on the union, complement, intersection, the difference for these following events. Part 1, it says we're looking for the event which is exactly one of the 3 events A, B, and C. Okay, one of the only one, exactly one of them occurs. Okay, not two, not none. Okay, not three. So I already draw a band diagram for A, B, and C. That's how it can happen. So it is what we usually use, except when we have some more information like A and B, they do not have any intersection, so we don't know here. So we generally, when we are going to talk about events like A, B, and C, we assume some intersection for the functions. So here you can see we have A, B is the right one, and C is the bottom one. This part occurs for both A and B. It's the intersection of A and B, and this small part here in between, it is the intersection of all the three sets A, B, and C. So now what we want here is exactly one of the three events occurs. So exactly one, so it can't be here, it cannot be here, because here means none of them occurs. Okay, and for example, if I just say, what about here? Here means A and B both occurs. Okay, here is part of A and B, so that means when an element, a number here occurs, that means both A and B occur. And what about here? So for this part also, you will see it means all the three ones occurs at the same time, so it's not what we're looking for. So what is the answer? The answer is where one of them, exactly one, so that's gonna be here. Okay, here is where exactly A happens, and here is where exactly B occurs, and here is exactly where C occurs. Okay, so if you look, what is it? So these three parts, it is, it's like we find A union B union C, all union of all the three, and we intersect and we subtract the intersections. So that's going to be for part one of the question. So it's going to be A union B union C, and we subtract the differences. Okay, so that's going to be we find the difference with the set A intersection B, this one union, and we also need to subtract A intersection C, where both A and C occur, and we also need to find the intersection of B and C, and eliminate this part from A union B union C. So that's going to be where, that's the notation, that's the expression for exactly one of them happens. Okay, exactly one of them occur. So that's part A. For part two of the question, okay, so they ask exactly two of the events occurs. Okay, so the part B was exactly one, so here is exactly two. Okay, now for this one, you can see here is where exactly A and B occurs. Okay, here is exactly A and C occurs, and here is exactly where B and C. So you need to know, okay, so here this part is not included because here is where all the three events occur, okay? So, but we are looking for the part corresponding to exactly two occurs. So here is A, B, and C, all the three occurs. So that means we only want this part. So what is the expression for this? We can write the expression different forms, okay? It's not unique. You can just look at the question different ways and do this one. For example, you can see from the union of A, B, and C, we eliminate part one of the question, which give us just only exactly one occurs, and also eliminate the intersection of all the three. Or we can just find, so we can say, okay, for part two, we find union of A intersection B. Okay, so here is the intersection of A and B, intersection of B and C, intersection of A and C, find union of these three, and then remove this intersection of all the three. So it's going to be A intersection B, union A intersection C, union B intersection C, and when we find the union of intersections, so that means so far what we have is just this part including this middle part, and we remove this part from this union, so it's minus A intersection B intersection C. Okay, what about the third part of the question? So it says one or more of the events occur. Okay, so the first one was exactly one, so it is just these three parts. The second part is exactly two of the events occur, so it's just intersection of AB, intersection of A and C, intersection of B and C, minus the intersection of all the three events. Now here it says for part C, one or more of the events. So that means maybe A, maybe only B, only C, A and B, A and C, B and C, or maybe all the three. So it says at least one. From this description, so it's obvious that the events that at least one of them, at least one or more, at least one events occur. So it's just the union of all the three events. So that's going to be where at least one of these events occur. So you can see here is only A, only B, only C, A and C, A and B. Here is B and C, and this part is the intersection of all the three events, which means all the three events occur at this part. So the answer for part 3 of the question is A union B union C. So union of three events, n events, is just, you can see it can be described by this: one or more of the events occur, and it can be also at least one of them. So we can have at least one of the events or one or more. So it is a description of union of some events. Okay, so the fourth part of the question is two or more. So here we're not looking for the parts which exactly one part occurs. So it's just, what we're looking for is just two or more events occur, two or more. Now you can see here, this part, it is where exactly and only A occurs. Here is exactly only B, here is exactly C, where A, B, and C, at least two of them occurs, two or more is this part. So we can just two or more is going to be, here is A and B, here is A, B, C, here is A and C, here is B and C. Any other part of this diagram is less than 2 event. Okay, so here is where 2 or more. Now if you're going to describe it mathematically based on union and intersection, it's going to be it's A intersection B. We have here is A intersection B, here is A intersection C, and here is B intersection C. So, and that's the union of all the 3 parts. This part is the intersection of all, which includes in all the 3 intersections. Now we don't need to just write it separately, so we just have A intersection B union with intersection of A and C union intersection of B and C, and that this expression gives what we're looking for, where at least 2 events occur, at least 2 or 2 or more. And the 5th part is none of the events occur. Okay, none of them. So where is it? It is, you can see any point inside here, we choose at least one of the events occur. Okay, any point here, okay, will give us at least one of them. So, and we don't want any of these events occur, so that means the solution set, the part we're looking for is where it's not here. So where is it? It's outside of this. Okay, so it's going to be outside of A, B, or C. Here is, and you can see what we're looking for is actually the complement of union of A, B, and C. Okay, that means the event which none of them occurred, that means outside of all the 3 events. So the 5th one is, we find first A union B union C, and then its complement is what we're looking for. In computer science, a byte is an ordered set of 8 binary characters, namely bits, used in most machine languages. Each of the binary characters is either the value 0 or 1. Okay, so for values we have 0 and 1, 2 values, and each byte has 8 characters. Now, what is the first part of the question? It asks how many different bytes can be formed. Okay, so in this type of question, you can see there's no restriction. They didn't mention there's no restriction, but they also didn't put any restriction on the question. So that means, okay, so generally how many bytes can be formed? Okay, there's no restriction here. This part is easy. We have 8 places, so that means there's order, there's no restriction, so that means we have repetition. A digit 0 or 1, it can be repeated. So we have 8 places, so you can see 4, 5, 6, 7, 8. For the first digits, there are 2 options, 0 and 1, the same for any other. So it's just 2 times, which is 2 to the power of 8. So like any other situation which we have order and we have repetition, so the answer is 2 to the power of 8, k to the power of n. Okay, what is part B? Part B says, okay, now there is a restriction on the question. In part B, it says how many bytes can be formed if the first byte is 1. Okay, so here's the restriction is, okay, again, it's a byte, 8 places. So for the first one, it says the first bit is 1. So there's just one option here. We don't have 0 here. And for the second one, it can be any of those two. So it's just 2 times 2. So it's just 1 times 2 to the power of 7. 3 friends, Al, Bob, and Chris, put their names in a hat, and each draws a name from the hat. Assume Al picks first, and then Bob, and then Chris. Now we're gonna find the sample space for this event. Okay, so for part A, let's say we are going to show that Al with A, Bob with B, and Chris with C. Okay, so what is this? So the sample space S would be it can be A, B, C, or A, C, B. So what does it mean? It means, for example, here Al picks his name, and then Ben picks Chris's name, and Chris picks Ben's name. Okay, so the first component is what Al picks, the second one is what Ben draws, and the third one is what Chris draws. Okay, now what is the next? It can be B, A, C, and B, C, A, and the other one, it can be C, A, B, and C, B, A. Okay. 6. It can be in 6 forms. But why is it 6? So actually, it is. We have 3 choices. The first one is what Al draw. The other one is what Ben draws. The last one is what Chris draws. So there are 3 choices for Al. Multiply. So 2 for Ben, and the last one remains for Chris. That is just 6. So NS is 6. So, and you can see we found the 6 form of drawing names. Okay, that's for part B. For part B, it says find the sets A, B, and C. Okay, we're gonna find 3 events, 3 sets corresponding to the events. Event A is Al draws his name, event B is Bob draws his name, and event C is Chris draws his name. Okay, so that's easy. We just, what is A? So maybe here is better I just change these letters to small letters to be different from these events. I can say, okay, it's A, B, C, A, C, B, B, A, C, B, C, A, say this one is A, this one is B, and this one is C. Okay, so now what is the event A? That the event Al chooses his name, so that means, okay, here the first component is the name which draws by Al, so here is, so it should be A. Okay, so here and here, these two will form A. So A B C and A C B. So what is B? So the second component must be B. So it is A B C and C B A. What's C? Okay, the third component must be C. Okay, you just look at the 6 triples and we choose the one which the third component is C. So A B C and B A C. Yep, these are the events A, B, and C. Okay, now what about part C? It says find the set corresponding to the event. No one draws his own name. Okay, so what about this now? You can see here A, I'll draw his name, so it's not part of the answer. This one is not. This one is not because Chris draws his name. This one can be. Okay, for parts C of the question, let's say it is the event D. So it can be B, C, A. So Al draws Ben draws Chris, and Chris draws Al. Okay, so no one picks his name. So what about this one? This one is also an answer because Al draws Chris, Ben draws Al, and Chris draws Ben. Okay, so different names. So it is C, A, and B. And the last one is not. Okay, the last one is not because Ben draws his name, so it can be an answer. So that's the event D. Okay, part D, it says find the set corresponding to the event everyone draws his own name. So that's an easy one. So part D, the event E is I'll draw his name, so it's just A, Ben draws his name, B, and C is Chris. So just one element. Okay, so everyone, so it says everyone draws his own name. Okay, so there's only one choice. Okay, if just Al his name, Ben his name, Chris, so A, B, C is the only answer for part D of the question, which gives us the event E. The next part, find the set corresponding to the event one or more draws his own name. One or more. Okay, so it is a bit different. So part D says everyone draws his name, so there's only one choice, A, B, C. But here it says one or more. Okay, it doesn't say everyone. It can be only 1%. Okay, so if you just look at this set, so you can see the first one can be because A, B, C, all the 3% choose their own name. This one can be A selects its name. This one can be Chris draws his name. This one cannot. Okay, no one draws his name. And this one, no one draws his name. And this one also can be. So if you can just log this part E is actually the complement of part C. Part C says no one draws his own name, but part E, it says one or more draws his own name. So that means these two are complement of each other. Okay, so you already have the answer for part C, which is these two, and subtract this set from the sample set space. It will give you the solution for part E of the question. So it's going to be set F. So it can be ABC, ACB, BAC, and BCA. BCA cannot be. Okay, so then CAB is not also, but CBA is a solution. Okay, so here we can see here A, B, and C, all the 3% draws their own name. Here A draws his name, here C, and here B. Okay, so that's the answer for part E. A die is tossed if the observed number is 1 or 4. We toss it again, otherwise a coin is flipped. Okay, so what is this experiment? It has two parts. Okay, so the first part is tossing a die. Okay, so when we toss a die, we have 6 options, we have 6 outcomes, the numbers 1 to 6, and depending on the result of first action, first event, tossing the die, we're gonna have a second event. Okay, depending on the result. If the numbers in the first die are 1, 4, or 4, then we toss the die again. Otherwise, we flip a coin. Now, part A of the question, it says write the sample set for this experiment. Okay, so here we can talk it based on the as a set. It's like we need to use order pairs because there are 2 results. Okay, depending on what is the result of the first one, we're gonna have a result for the second action. Okay, it might be flipping a coin or tossing another die. So what is the sample set? S is, okay, if we have 1 for the first die, okay, when we toss the die, if this 1, then we're going to toss another die. So it's going to be, so the result of the second die might be 1. So it can be 1, 1, 1, 2, 1, 3, or 1, 6. Now, what about 2? If we toss the die and the number showed up is just 2, so that means this time we flip a coin and it can be tail or 2 in head. What about 3? 3 the same. Okay, again, after 3 we're gonna flip a coin, so it might be 3T, 3H. What about 4? For 4, we toss a die. So it's just 4, 1, 4, 2, 4, 6. For what about the other numbers like 5 and 6? For 5 and 6 also we flip a coin, and we are going to have 5t or 5h, and for 6 it might be 6t or 6h, and that's all the outcomes, all the results in this experiment. How can we count ns without writing the sample set? So here maybe it's better we talk about the counting the numbers after solving part B of the question. Okay, so part B says draw the tree diagram for this experiment. Okay, so it was the set S, the sample set. Now we are going to talk about, so it is part A. For part B, let's draw the tree diagram. For tree diagram, for this first action, first event is just tossing a die. So we have six options. 5 and 6. Okay, so here let's say it's 1, 2, 3, 4, 5 here and 6 here. For 1 and 4 we toss a die again, so here is 1. So again 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. For 2 we're gonna have H and T. For 3 also we're gonna have H and T. For 4 again 6 options. For 1 because we toss a die again. 1, 2, 3, 4, 5 and 6. 5 and 6. For 5 and 6 again we have head and tail because we flip a coin. Head and tail. Okay, so that can be the tree diagram for this one. So now we can count the numbers. Okay, so here we have the sample set. When we write down all the outcomes, we have the tree diagram, but how can we count the number of elements in this sample set, in this event, without writing down the sample set or drawing the tree diagram? To do this one, what we need to analyze what's happening here. There are two jobs, okay, so the first one and the second. So for the first one, these two jobs must be happened, okay? You know, it's not like we have one job and we cannot do the second one, okay? So there are two jobs, which is the first one. The first job is tossing a die, and the second task is, it depending on the result, it can be any of those other jobs, tossing a die or flipping coin. But we have two options, two cases which they cannot happen together, okay? Which is if the result in the first task, tossing a die for the first time, if the result are 1 and 4, the second task will be different from when the result are 2, 3, 5 and 6. So how can we count it? We can say it is we have two cases. The first one is for two results in the first action, okay, like 1 and 4, if we have 1 and 4, then we're gonna have 6 result for the second action, second task. So it's just 2 times 6 for the first situation, which is we have 1 4 in the first die, so therefore we're gonna toss another die, and it's just 12 situation. Okay, 2 times 6 is 12. And the other one is if any of those other numbers like 2 and 3, 5 and 6 happens in the first die, so then we're gonna flip a coin, and the result must be 2. Okay, head or tail, and it's just 8. You can see here this 2 is for the 1 and 4 in the first die, and this task will be followed by another task which is tossing another die. That's why these 2 tasks will happen together, okay, right after each other. So that means 2 times 6, the 2 must be multiplied by 6. That's a multiplication principle. But here, and the same thing here for the other 4 numbers like 2, 3, 5 and 6, the second task will be flipping a coin, and that's what happens. But you can see these 2 cases, having a die for the second task and having a coin for the second task, okay, they cannot happen together. So that's why we are using the addition principle. So ns will be 2 times 6 plus, here is plus, we're using addition principle, 4 times 2, and the result will be 20. So ns is 20. So we need to use both multiplication principle and addition principle to count the number of elements in sample set. Okay. Part C of this question is find the event of observing tail in the flipping the coin. So we can just take a look at the sample set and just pick the elements in this event. What we need tail in flipping coin. So it happens here, here, and 1 is here. So for any of those numbers 2, 3, 5 and 6, we're gonna have a tail in the flipping coin. So what's the answer? Part C of the question, the event A is 2 tail, 3 tail, 5 and tail, and 6 tail. So that's the event we can have tail for the flipping the coin. In how many different ways 10 people can stand in a line if there is no restriction, if 2 of them are going to stand next to each other, and the last part is 2 of them do not want to stand next to each other. Okay, to solve this one, part A, there are 10 people. They're going to stand in a line, and okay, all these 10 people are going to stand in a line. So there are 10 places. Okay, in this question, we have an order. Okay, the places are different, and the other thing is we don't have repetition. Okay, if somebody stand in a line, he cannot stand again. Okay, so that's part of the nature of this question. Okay, we have an order and there's no repetition, so therefore mathematically the solution is 10 factorial. Okay, but you can see for the first place we have 10 choices. Any of those 10 people can stand here, and then 9 of them, because already one of them has been stand at the first place, so just remain 9 people. So any of those 9, then 8 of them can stand here because already 2 of them are here. And in the same way we have 7, 6, 5, 4, 3, 2, 1, and that's a line, so these 10 people will stand in a line at the same time, so it's going to be multiplication principle. That's why I'm using multiplication between these numbers, and therefore the solution is 10 factorial. Okay, so first part was easy, just 10 factorial, no restriction on the question. It is the answer. Okay, so what about part B? For part B, 2 of them, let's say A and B, okay, A and B, they're going to stand next to each other. Okay, they didn't say where, but they're going to stand next to each other. It's like we can just say we have, instead of 10 people, we have 9, which one of them, you know, like we have 10 people, like A, B, C, D, I, and J. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, 10 people. They're supposed to stand in a line, and we are going to have A and B next to each other. Okay, how it can happen? So we can say here, we can say we have actually here assume there are 9 people, J, I, H, G, F, E, D, C. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and the 9th one is A and B. Okay, so we say we assume A and B, they're just one person. Okay, they're one person. We choose how these 9 people, okay, one of them is AB, they stand next to each other in a line, and at the end we choose where A is and where B is. Okay, because for A and B we have 2 possibilities. It can be A then B, or it can be B, it can be B and then A. Okay, so there are 2 possibilities how A and B stand next to each other, so we will talk about it later. So now, for example, okay, for example, one of the ways these 10 people, they can stand next to each other, and they can stand next to each other, and A, B be together. Okay, so one of them is this. One of those situations is this. I can say, okay, we have 9 places, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let's say I'm saying A and B, they stand here. Okay, and then the other 8 will be here, and then when we choose A and B are here, then for any arrangement of the other 8 people here, for example, I can say like C here, D here, I and J, and I know A and B will be here. So for any arrangement for these 8 people, here, there are 2 possibilities for AB. So it can be AB and it can be BA. Okay, so it can be C, we can have C, D, A, B, E, F, G, H, I, J, or it can be C, D, B, A, and then E, F, G, H, I. Okay, so for any arrangement of these 9 people, which one of them is AB, there are 2 possibilities for AB. So it can be AB and then BA. So here it can be for 9, when 9 people, they're going to stand in a line. So now there's no restriction here. I can say, okay, so it's just 9 factorial. In 9 factorial way, I can arrange 9 people in a line. And now we know that one of them is AB. That means there are two possibilities here. It must be multiplied by 2 factorial. So it is all the possibilities. We can have these 10 people in a line where when two of them, like A and B, they're standing next to each other. Yeah. So that's the answer for part B. What about part C? Part C, it says if two of them do not want to stand next to each other. Okay, so it is the complement, this event, part C, it is complement of part B. So part B, we want two of them stand next to each other, and we count all the possibilities, all the arrangements which two of them, A and B, they can stand next to each other in this line. Now I'm going to find all the other arrangements, okay, which these two won't stand next to each other. There are two ways to count these numbers, okay. One of them is directly. We just say, okay, A and B, they do not want to stand next to each other, okay, so maybe A can be here, then there are so B can't be here, so I just count the other numbers. What happens if B is here? So it takes time, and there are too many computations here, but the easy way is we use the complement formula. We can just simply say so n A complement is ns, this the sample space, minus n A. So we use this one. We already know ns is 10 factorial, all the arrangement of these 10 people in a line, so it's 10 factorial. Minus, and NA, A is when two of them want to stand next to each other, and I'm going to find the complement of that, which these two people do not stand next to each other, so it's just minus the answer of part B, which is 9 factorial times 2 factorial. How many different words can be made by the letters of the word probability? We already solved a word making question with the letters of the word history. Here the difference is the letters are not different. So we have B twice, and we have also I twice, one here, the other one here, and you can see the other letters are different. So if the letters were different, like the word history, it was the number of letters factorial. So history, it has 7 letters. How many letters? It's just 7 factorial. But what about here? It says we're going to use these letters. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We have 11 letters, but only B and I, they can be repeated twice in the new word we're going to make. So how can we solve this? We are going to use both word making technique and also the formula I gave in the last question. We said when we have n objects, and like n one of them are, like we have n factorial object, n objects, n1 of the same first type, n2 of the second type, and nr of the rth type. So the formula is n factorial by n1 factorial, n2 factorial, and nr factorial. So that was the formula for this type of question. So it is actually the same as here. We have 11 objects, n is 11. We have 11 letters. For P, R, Z, O, A, L, T, and Y, we have only one of them. So it's going to be N1, the number of P we're going to use is just 1. For R, it's just 1. For O, it's just 1. And when we divide it by 1 factorial, it's like just divided by 1. It's nothing. So we just use the number for the letters we use more than once. So it's like we have N1, the number of times we are using B. We can just say N of B instead of N1. N of B is 2. That means we must use B twice. And there's I, N of I is also 2. So now, how many different letters? So it can be N factorial divided by NB times factorial times NI factorial. And you can also say, okay, divide by NP factorial and so on to NY. But NP is 1, NY is 1, so it doesn't make any difference. So we can just simply remove this one and just consider the words which they must be used more than once. So like B and I are the only letters here. What is the answer? It's 11 factorial divided by 2 factorial and 2 factorial. How many different words can be made by the letters of the word history? Okay, so there are two types of word making question in probability. One of them is they're giving some letters, like, okay, they're just saying, what if we have these letters A, B, C, and D, and now how many words we can make with these 4 letters? Okay, so that's here we can repeat the letters, okay, if there's no restriction on the problem. So it means we can repeat the words, so repeat the letters. So that means how many words? 4 letter words. It can be 4 times 3 times 2 times 1, or if there's no repetition, if there is no repetition, it's just 4 3 2 1 multiplication. If there's no restriction, it's just 4 factorial. Okay, but the other type of word making problems here is when they give a word like history and they say, okay, now how many words can be made by using the letters of this word. Here they didn't mention how many letters that new word must have, so when they don't mention, it means it must have the same amount of letters as history, like 1 2 3 4 5 6 7. And when they're giving this letter history, it means you need to use these letters and exactly the same amount of times this letter used this word used those letters. Like H has been used once, so you can use it only once in the new letter, and I the same as once. So here you can see the letters are different. So we have 1 2 3 4 5 7 6 7, so we have 7 different letters. We are going to make a 7 letter new word. There's no repetition here. Okay, each letter can be used only once. So that's the difference. If they give this question in this way, how many letters can be made by using these letters H, I, S, T, O, R, and Y? And they can say how many words can be made by the letters of history. What is the difference? Here you can repeat, if there's no restriction, you can repeat the letters, and they need to mention how many letters exist in the new word. Okay, so for example, how many 7 letter words can be made? So here the answer is 7 times 7. It's like 7 times 7 times 7, it's 7 to the power of 7. Now let's back to our question here. When we have the word history and we are going to make 7-letter words. So here again it's supposed to be a 7-letter word, 3, 4, 5, 6, 7, because it's a word, so therefore we have order. We have the first letter, second letter, seventh letter, but the difference here is for the first place, for the first letter, we can choose any of those 7 letters. It's 7. But what about the second? Because there's only one letter of each, so here remains 6, and then 5, 4, 3, 2, 1, and then we multiply these numbers, and it's going to be 7 factorial. How many 5-digit numbers can be made if part A is there's no restriction? Okay, so it is like we're going to make words, okay, with some given letters, but here we're going to work with digits. For part A, how many digits we have? We have 10 digits, 0 to 0, 1, 2, 9. There are 10 digits. Part A, it says there's no restriction. Okay, so that means 0 can be first digit, these numbers, they can be repeated. Okay, so but we have order, okay, for numbers, for words, for books in the shelf. So we have, for people stand in a line, we have order. Okay, so we have places, and so for this one we have 5 places, and we have repetition. Okay, these digits, they can be repeated. So for the first one we have 10 choices, any of those 10 digits, and then 10 here, 10, 10, and 10, and then we multiply them, so that's going to be 10 to the power of 5. So if it says, okay, each digit can be used only once, so now it's going to be different. So it's just 9 times 10 times 9 times 8 times 10, 9, 8, 7, and 6, okay, which is 10 factorial divided by 10 minus 5. Okay, what about part B? Part B, it says the numbers are even. Okay, for even numbers, the right digit must be an even number, like 2, 0. It can be 0, 2, 4, 6, and 8, any of these 5 digits. So we have 5 places. Okay, the only restriction on the question is it should be even, so still we have repetition, but for the right digits right here we have only 5 choices. Okay, and even digits like 0, 2, 4, 6, and 8. So here it can be 5, but what about the other 4 digits? They can be any of those 10 digits. Okay, they can be repeated. So here is 10, 10, 10, and 10. So it's 10 to the power of 4 times 5. Part C, it says the numbers are multiple of 5. So when we're going to have a number multiple of 5, so the right digit, it must be 0 or 5. So it's exactly like part B of the question, but this time here we have only 2 choices. It can be 0 or 5. Okay, so it's just 0 or 5 now, but for the other digits it can be any of those. 10, 10, 10, 10. Okay, we are going to have 5-digit numbers. So for 5-digit numbers, maybe if it's going to be a 5-digit, maybe here we can just choose the first digit. It can be 0. Okay, maybe we can say here is 9. So because if it's 0, we're gonna have a 4-digit number. Okay, we can just ignore the left digits if it's 0. So we just give this 9, and so the first one, it can be 9 times 10 to the power 4. The other one is just 9 times 10 to 3 to the 3 and times 5. So the last one is just 9 times 10 to the power of 3 times 2. So what about part D? Part D, it says the first and the last digits of the number are the same. Okay. Okay, so here we have, for the first letter, the left one, we have 9 choices, 1 to 9. For this one, we have only 1. So, okay, we are using exactly the same letter as we used here, so there's only 1 choice here. And what about the other 3 ones? Here we can use any of the other 10 letters. Last part of the question, the number is made only by 1, 4, 5, 7, and 9, by only these digits. So here, that's an easy one. 5-digit number, and it can be 5 here, 5 here, 5 here, 5 here, and 5 here. So it's just 5 to the power of 5. In how many different ways 10 objects in 3 types A, B, and C can be arranged in a line if 2 of them are of type A, 3 of them of type B, and 5 of them of type C? And we know, okay, more information, there is no difference between the objects of the same type. So that means the objects, we have 2 objects of type A, so that means those 2 objects of type A, they're exactly the same, okay, like 2 books of the same title, okay, the same subject, the same title, so they're exactly the same objects, and we have 3 of them of type B and 5 of them of type C. So how can we do these type of questions generally? The formula is, when we have n objects, and we have n objects, n1 of them of type 1 and 2 of type 2, and we can say n r of them of type r. What is the formula? How many arrangements we have for this one? So when it says arrangements, it means like making a board. It's like put some books in the shelf, on the shelf. So there's an order, okay? There is an order here. There are some repetitions because we are assuming 2 of them are of type A, so that means, you know, that object can be repeated twice, and the objects in type B, there are 3 of them, so it can be repeated 3 times, and 5 of them are type C, so these objects can be repeated 5 times. So we have repetitions in each object of different times, and the formula is, for this one, all the total number of arrangements, it's n factorial divided by n1 factorial, n2 factorial, and nr factorial. If I'm going to explain this formula, it says n factorial is actually when we have n different objects. when all the n objects are different, there's an order, there's no repetition. So if you're going to find all the arrangements, so that's going to be the permutations. It's just n factorial when they are different. But let's say we have n1 of them of the same time. They're exactly the same thing. So that means, like, let's say we have A, and B, three objects, and we are going to find all the arrangements. So if this one is the first A and this one is the second A, there is no difference between when you put the first A here, second A here, or you put the second A here and then first A. There's no difference between these two, and we must eliminate this repetition, these two similar things from the countings. So here we can say, instead of 3 factorials, because there are no 3 factorials, there's actually 3 factorials divided by 2 factorials, which is 3 different ways we can just put this A, and B. So what are those three arrangements? It can be A, B, it can be A, B, and it can be B, A. That's all the 3 forms. We can just put these 3 letters A, and B next to each other, okay, like a word. So here you can see it should be 3 factorials, but 2 factorials, 3 is n. We have 3 letters, and 2 of them are exactly like they are the same. Okay, they're the same type. Now, how can we do this question? Okay, so n here for our question, n is 10 objects. N1, the first type, is A, so we have 2 of them, so N1 is 2, N2 is 3, and N3 it's 5. So we have 3 types, 3 groups, and what's the answer? The answer is n factorial, which is 10 factorial divided by 2 factorial, n1 factorial, n2 factorial, which is 3 factorial, and n3 factorial, which is 5 factorial. In how many different ways 5 people can stand in a line and can sit around a circular desk? So for this question, there are 5 people, and we are going to solve the question for 2 different scenarios, and in each part we have to solve it with different perspective. For part A, 5 people, they're going to stand in a line, all 5 of them. It's easy, there's an order, 5 places for 5 people. There's no repetition. The answer is 5 factorial. The reason is it's just 5 times 4 times 3 times 2 and 1. So that's easy. It's just 5 factorial. There's an order, there's no repetition. The answer is 5 factorial and factorial. That's easy. What about part B? Part B, these 5 people, they're going to sit around a circular desk. So what is the difference here? Let's say we have a desk. Now, these 5 people, they're going to sit around the desk. So what is the difference here? If I say A is here, B, C, D, and E. They sit around the desk. What is the difference between this and I say B sit and then C and then D and then E and then A? You can see here at first A sat around the table, and then B and then C, D, E. But the second time B was the first one who sat around the table, and you can see again we got the same way. Okay, so they're not 2 different ways, because if you can just look, it's A again, then B, then C, D, E. Okay, so you can see it's a little bit different than sitting around the table. For doing this, how we can solve this one is just, we can just say, okay, we have a circular table. First, we say, okay, here is the table. Here is the beginning. We choose a beginning, we choose the first place here, and we say, okay, let's one of those 5 people sit here. Doesn't matter which one. Okay, let's say A. And then based on that, we say, okay, now it's like a line. It starts from here, and not 5 but 4 people are going to sit around the table. Okay, A is just the origin here, and then we kind of make a line of 4 people. Okay, B, C, D, and E, and all the different options, all the different ways these 5 people they can sit. It's like how these 4 people they sit next to A around the table. So the answer is, actually we have 4 places and 4 people. They're going to sit at these 4 places. It's like now it's like a line. So the answer is 4 factorial. So for sitting n people around the circular desk, the all the total ways is just n minus 1 factorial, which is 5 here minus 1 factorial. That's how we can solve this one. The combination to a padlock is given by 3 numbers from the numbers between 0 to 59. For example, a possible sequence would be 2 to the left, 24 to the right, and 18 to the left. So the sequence is left, right, and left, and there are and the numbers must be between 0 and 59. So that means for each number it must be, we have 60 choices. How many different combinations are there to open such a padlock? Okay, so what if we have a padlock, we don't know what is the combinations, and we're just gonna try all the possible numbers, okay, possible situations, and all the possible combinations, and here we're gonna know how many times we have to try. So there are 3 numbers, there's an order, there's combination, there's a repetition. So that means for example, it can be 2 to the left, 2 to the right. Okay, so these 2 can be happened twice or 3 times. So for the first one, how many numbers we can try? It's 60, any of these numbers between 0 to 59. For the second one is also 60, and the last one 60. Order, we have repetition, so it's 60 to the power of 3. A lecture room has 60 seats. In how many ways can 45 students occupy the seats in this room? Okay. So here we have 60 seats. So for this question, it's important how to think about solving it. We can say, okay, we have 60 seats. For each seat, how many choices we have? So it is the wrong way to think about this question. Okay, the right way is we have 45 students, and then for each student we choose a seat. So that means we have 60 objects. We're gonna find an arrangement of 45 of them. Okay, there is an order, there's no repetition, so therefore here we have n equals 60 and r is 45. So what is the total amount of ways? So it's going to be 60 factorial divided by 60 minus 45 factorial. Okay, so that's how we solve it using the formula. But what is the logic? So we have 45 students. Okay, so first student, second, third. Here is the first student, second student, third student, and so on to the 44th students and 45th students. How many choices here? So it's going to be 60. Any of those 60s, the first students can choose any of those 60 seats. For the second one, it's just 50, 59, it's 58. Okay, so and so on. Okay, so it goes to 60 minus 45 is going to be 5. 5. Here is 6 and 7. Okay, and we just multiply these numbers. Okay. In a 52 card deck, in how many ways 2 cards can be drawn from the deck with replacement if? Okay, so first of all, we have replacement here. So it's with replacement. Okay. So let's see what is a 52 card deck. So here we have 52 cards. You can see there are 4 groups of cards: club, spade, heart, and diamond. And each group has 13 cards in. It starts with ace and 2 to 10, and we have jack, queen, and king. You can see heart and diamond are in red, and club and spade in black. Okay, so we are going to draw 2 cards from these 252 cards. Part A is with no restriction. Okay, just and it is with replacement. That means we draw the card, we put it back in the deck, and we pick the second card. Okay, so that's easy. It's just we have 2 cards. For the first card, we have 52 choices. And how many for the second one? It's again 52. Because when we pick the first one, we have 52 choices. We put it back in the cards, and for the second one, we again have the 52 choices. So the answer is 52 by 52, which is 52 squared. Okay. Part B, both cards being red. Okay, so we are going to draw 2 cards, and both cards must be red. Again, we have replacement. Replacement is a condition on the whole question, okay, for all the 4 parts. So how many red cards do we have? We have 2 groups of cards. They are 13, heart and diamond. So which is 26. We have 26 choices for the first one, and 26 for the second one. So that's going to be 26 squared. What about part C? Part C says the first card is red and the second one is heart. Okay, so we have a kind of a condition. So 2 choices. For the first one, it must be heart, but it must be red. First card is red, the second one is a heart. So first one, heart, red, we have 26 choices. There are 26 red cards, and then the second one is heart. So how many heart? There are 13 heart cards. Okay, 13. So it is 26 for the first one, and multiply by 13, which is, how many hearts we can draw. So the next part is picking a red card followed by club. So now again we have two cards. The first one is pick a red. So if it's gonna be red, red card for the first one, followed by a club. So red cards 26, and how many clubs? We have 13 again. So that's it. So let's do another card problem. So here again we have 52 cards. Now we are going to again draw two cards from this 52 cards, but this time we have the situation of without replacement. So previous question, the last question, it was with replacement, but here we have without replacement. So what happens when we change the replacement bit without replacement? So part A, it says there is no restriction. Okay, so we do not have replacement and we do not have any other restriction on the question. So here again we are going to choose two cards. For the first one we have 52 choices, but for the second one we have 51 now, because we already used one card for the first one and we do not have replacement. So one card has been eliminated from that deck of cards, so it's just 52 times 51, or we can formalize it by 52 factorial divided by 52 minus 2 factorial. So when we do not have repetition and we have an order, okay, so we use this formula. Part B, it says both cards being red. To have both cards red, so how many red cards we have? In total we have 26 cards. So it's again like part A of the question, but this time n is 26. It's not 52. So here we are going to have 26 times 25, which is actually 26 factorial divided by 26 minus 2 factorial. What about part C? For part C, it says the first card is red and the second one is hard. Okay, so here two cards. The first card is red. We have 26 choices, and now for this one, now we're gonna have the second card must be hard, and you can see the second card, if it's gonna be hard, so you can see hard is red also. Okay, so we need to solve this part by a trick. Okay, so let's part C. Okay, we have two options. Okay, the first card, it should be red. Okay, but the second one, so it has two options. It can be hard or it can be a diamond. Okay, so if the first card is a hard, so we gonna have one of these 13 cards, then the second card must be how many? It's like 12. But what if the first card is a diamond? If it is diamond, for the second one we have 13 diamond, and for the second one we have 13 hearts. So two different options, and we use addition principle here. We have two parts. The first one is, what if the first card we draw is a heart? So it's going to be 13 for the first one, which is a heart, times, what about the second one? It must be hard. We already used one heart for the first card, it's just 12. That's the first part. Or what if we have here, we put plus here. The first card is a diamond. If it is diamond, we have 13 choices, multiply by how many hearts now? The first card was a diamond, so still we have 13 heart cards, so it's just times 13. And that's the answer. What about part D? It says picking a red card followed by a club. Picking a red card followed by a red card. So part D. So the first one is a red. The first one is red. The second one is club. So club is, you can see it's black. So if the first one is going to be red, so that means we have 26 choices, and no matter which one we choose from these red cards, for the second card we still have the 13 choices of the club. Okay, they're just in black. So here the answer is, for the first one we have 26 times and we have 13 for the second one, which is the number of club cards we have. In how many different ways 4 out of 10 people can stand in a line? So here we have 10 people, but there's a line which it has a capacity of 4 people. Okay, so we are going to choose 4 out of 10 people and arrange these 4 people in the line. So here it's not standing 10 people, it's just 4 out of 10. Here the solution is easy. For the question, it's a line, there's an order and there's no repetition, but we cannot say it's 10 factorial because there's no 10 places here. There are 4 places, so we have 1, 2, 3, 4. For the first one we have 10 choices, and if those 10 people, then 9 for the second, 8 and 7. So, and we use multiplication based on multiplication principle. So that's the answer for this part. But what is the formula for that? When we have n objects and we are going to put r of them, r out of n, in a line. Okay, when we have an order, we're going to make a word or a number. So when there's an order and we have n objects and we are going to use an object and there are places. So what is the answer? It's going to be n factorial by n minus r factorial. So that's the formula, and it can be used for this question. So it is n is 10 and r is 4. So we're going to have 10 factorial divided by 10 minus 4 factorial, which is 10 factorial divided by 6 factorial, which is exactly the same as 10 times 9 times 8 and times 7. You have 14 textbooks, including 3 linear algebra, 5 psychology, 4 sociology, and 2 economics. The books in each subject are identical. How many different ways can you place these manuals on a shelf of your library if there is no restriction? Okay, so here again we have another question for the formula we just talked about. We have 14 objects, 14 books, and in 4 groups. Okay, the books in linear algebra or psychology, sociology, and economics. And we have, for example, 3 linear algebra books, and these 3 are identical. They're exactly the same. Okay, there's no difference here. And the same happens for sociology, psychology, and economics. So we are using the same formula as the last 2 questions. Here n is 14 books, n1, the number of objects in the first group, linear algebra books, is 3. They must be the same. So the question already said, okay, they are identical. And okay, and there is an order because it's a library, into the number of objects in the second group. Psychology is 5 and 3 is 4, and N4, the last group, is 2. Okay, so the formula is n factorial divided by n1 factorial, n2 factorial, n3 factorial, n4 factorial. So it's going to be 14 factorial divided by 3 factorial, 5 factorial, 4 factorial, and 2 factorial. How many 7-digit telephone numbers are possible if the first number is not allowed to be 0 or 1? Okay, so the first number is not allowed to be 0 and 1. It has 7 digits. Okay, so here 1, 2, 3, 4, 5, 6, and 7. The first digit and the second digit, they cannot be 0 or 1. So we have 8 choices for the first one, from 2 to 9, and 8 for the second one. What about the third to the seventh? So they can be 10. So 10, 10, 10, 10, and 10. That's the multiplication principle. So that's going to be 8 squared times 10